All right, so yesterday I gave you this handout for assigning R versus S to various stereocenters, and we looked at Adderall as an example of the first one. And then we ended by talking about an example where the lowest priority was a wedge, and we said you have to flip R to S or S to R if your lowest priority is wedge. Let's go and do harder examples. All right. Yesterday, one of the drugs we looked at was ibuprofen, and I told you ibuprofen is sold as a racemic mixture. However, let's take a look at one of the possible enantiomers. So for this one, the methyl group that's coming off, I'm going to represent that as a dash. And that assumed hydrogen is going to be a wedge. So we do have a stereocenter coming off, and I'm going to label that with a star. First thing we want to do is we want to identify the heaviest attached atom, right? So if I look over here, I've got an attached carbon. If I look over here, I've got an attached carbon. And if I look over here, I have an attached carbon. We've got a three-way tie between carbon, carbon, carbon. However, we know hydrogen's the lowest. So let's just get the easy one out of the way. Okay, so hydrogen's number 4, but we've got this three-way tie. Like I said, if there's a tie, you need to continue going on down the chain. So let's take a look at what these 3 carbons are attached to, and I'll start with the carbon for the carboxylic acid. So the carbon for the carboxylic acid, what is that carbon attached to as we move away from the stereocenter? It's attached to this oxygen, so I'll label that. It's attached to this oxygen, so I'll label that. And because it's double bound to that oxygen, we actually count that oxygen twice. This is called a ghost atom. And we do this for the double bond. That would be a good Halloween costume. What are you? I'm a ghost atom. Ooh. All right, let's do the methyl group. What is the methyl group attached to? 3 hydrogens. All right, as we move away from the stereocenter, that is attached to 3 hydrogens. Easy enough. All right, and then last but not least, we've got that aromatic carbon, the one that's a part of the ring system. What's that attached to? Yeah, 2 real carbons and a ghost carbon. So we'll label that as a ghost carbon. So I just put brackets around it. Same idea. We have to account for that double bond, right? All right, so now the question is, which of these carbons is the higher priority? Is it going to be the carboxylic acid, the aromatic ring, or the methyl group? Carboxylic acid. Okay, so I'm just going to erase this to clean up my notes. You're welcome to keep it in yours. All right, so we said the carboxylic acid carbon must be carbon 3, or sorry, 2, or 1. Sorry, I'm getting all confused in my head. So that was the highest priority, followed by this one, followed by the methyl group. Okay, so now we're going to connect this with a line going 1 to 2 to 3. All right, so it looks like it's going to the right. Is it automatically going to be R? Why not? Yeah, because the lowest priority is a wedge, we need to flip it. So we'd say turn to right. To the right is normally R. But the lowest priority is a wedge. So we switch it to an S. So that would be the correct conformation for that stereocenter. Does that make sense? All right, let's do a harder one. All right, this one, I want you to check with your neighbor to see if you agree with them. I believe this is an arthritis drug that's not commonly used anymore. used to be used to treat chronic arthritis. I think it's like penicillamine or something like that. Not penicillin, penicillamine. All right, so we need to first identify the stereocenter. That's pretty easy. It's going to be right there. I want you to determine what the stereochemistry is. Is it an R or is it an S? And check with your neighbor. Yeah.
So when we get to the point where we have multiple stereocenters, like what do we do with them?
You got to identify all of them as R or S. So if you have more than one stereocenter, you got to label all of them as R or S. It's a lot of work. And then you incorporate it into the IUPAC name too. So we'll practice naming with stereocenters.
I'm trying to hate this organization.
All right, who thinks they got this one? Give me a thumbs up if you got it. Thumbs down if stereochemistry makes no sense to you. Sideways thumbs if you're a little uncertain. There's somebody going like this. I don't know what that means. Right. So let's zoom in on this. We've got our stereocenter identified with the star, right? That's my first step. Then I'd say, all right, what's the heaviest attached atom coming off this stereocenter? Nitrogen. That's pretty easy. All right. Lowest priority is going to be hydrogen. So let's get that out of the way. However, we've got a carbon-carbon tie, right? So position 2 and 3 isn't immediately clear. So let's start with the carboxylic acid. What's attached to that carbon as we move away from the stereocenter? 2 real oxygens and a ghost oxygen, right? Makes sense? All right, then we do the other carbon on the left-hand side. That's attached to a sulfur, carbon, and a carbon, right? As we move away from the stereocenter. So then we go to the tiebreaker rules. Did you notice how when I lined up my atoms, I lined it up sulfur, carbon, carbon? You want to line them up going from heaviest to lightest in general. And then I'd say, all right, let's compare the heaviest atom coming off that carbon, which is sulfur, to the heaviest atom coming off of this oxygen, or this carbon, which is oxygen. Sulfur is heavier than oxygen, right? So in this case, the heaviest next attached atom wins. So it's not the sum. It's just the heaviest next attached atom. So this carbon on the left has the heaviest atom attached to it, being a sulfur. The carbon on the right, the heaviest attached atom is an oxygen. Sulfur weighs more than oxygen, therefore it wins. So we're going to label this as priority 2. This one as priority 3. So again, just like before, we're going to have an arrow going like that. So we're going to the right. Is this automatically going to be an R? Why not? Yeah, your lowest priority is wedge. So this would be an example of our S conformer. So lowest priority is a wedge. So we flip R to S. Was there a question in the back? Yeah. Yeah, the ghost atom just accounts for the double bonded carbon-oxygen bond. So you count that oxygen and that carbon-oxygen bond twice. One for the real oxygen, and then we count a ghost oxygen for the double bond. Yeah. Yep.
So does the ghost atom do anything other than just get a special name because it's a special snowflake?
Yeah, it doesn't do anything. The question was, does it do anything? No, it doesn't. It's just used for assigning priorities. That's all it's used for. All right. So it is tricky. I really recommend doing practice problems with these. Try to do as many as you can from the book. Once you do them a certain number of times, it tends to click, but it takes a fair amount of practice to get there. So try to do ones that look really different. Try to not do ones that look the same all the time. All right, yeah?
When you're going farther down the chain for equal whatever, and like the first farther down the chain is also the same, or like if they're similar down the chain, like where at any point does some make a difference, or like is it just at some point one of them is?
Yeah, that was a good question. So the question was, what if you still have a tie after you move out? Then you go to the next carbon out, or next group out, and then next group out until you find a difference. Once you find a difference, that's what takes priority.
What if they
Good
are
question.
the same?
If they're all the same, then it's not a stereocenter, right? Because you have to have 4 different groups. Yeah, so that's a good question. All right, so now I've got a challenge one. And this challenge one drives students nuts, and every textbook has a different way of explaining it. I explain it differently than the Klein textbook. So let's do this one. All right, so for this challenge one, I've got this compound. I'm just kind of making one up. All right, this is a chiral compound. It has a stereocenter, no internal plane of symmetry. What's the highest substituent? Most important. Which one? Chlorine. All right, so chlorine's number 1. Number 2? Fluorine. Number 3? Oxygen. Number 4? Carbon. Right, we don't have a hydrogen coming off of there. All right, so now we can go ahead and we could say, all right, go like that. Our lowest priority isn't a dash or a wedge. What the heck do we do? All right, I'll show you a trick. So in this case, we've got a problem. Our lowest priority is not a dash or a wedge. All right, the solution is to draw a Newman projection. Looking down the lowest priority bond. All right, so let's say we've got our little stick man. He's going to be looking straight down that bond, right? So let's redraw this as a Newman projection. We're going to have 3 branches, and really we're only concerned with the front group in this situation, right? So what's going to be sticking straight up? The fluorine. What's going to be to the bottom right? Chlorine. Bottom left must be the alcohol. All right, so I'm only drawing the front half of this Newman projection, but that's fine. We said chlorine is priority 1, fluorine's priority 2, oxygen's priority 3. We don't care about the carbon, it's priority 4, and it's assumed to be behind, right? So now that we've done that, we can do our arrow connecting, and we'd say, all right, we're going to the left. So what would this be, knowing that carbon's now in the back?
Saudi Arabia.
The S, right? So if we look at this, left-hand turn, lowest priority in the back, this must be an S stereocenter. So what I always tell students is Newman projections are in many ways pretty helpful for solving some of these when your lowest priority is in a dash or wedge. It's not immediately clear what to do unless you have the perspective of looking down that lowest priority bond. Yep.
Does it matter which direction we look down the lowest priority bond? Should we look from the stereocenter down
Yeah.
the bond or from the bond?
That's a really important question. So in this case, I always recommend looking down through the stereocenter where your lowest priority is in the back. That way you don't have to do any of that flipping nonsense. It's just automatically, if you're going to the right, it's R, and if you're going to the left, it's S. So Newman projections can help clarify that a lot, right?
Isn't
Yeah.
it going to be always S?
Uh,
Because you're looking at the perspective where the 4th one is at the back.
Yeah, so this is how I've got it drawn with that stereochemistry is always going to be S. The problem with some of these, though, let me show you why this is a problem, I guess. To explain why we would do this is it kind of depends on how you draw it. let me zoom in on this. And this is kind of a crummy drawing, but you get the idea. So you see how both of these are the same molecule? OH is a wedge in both of them, chlorine's a dash in the other one. The problem, again, comes from the fact that, all right, if you do this one as 1, 2, 3, it looks like it's going clockwise versus this one being 1, 2, or sorry, the first one was counterclockwise versus this one that's going clockwise. It's kind of ambiguous, right? So which direction takes priority, we don't know until we do the Newman projection view, and then it's more clear. Does that make sense? It's the exact same molecule. It's just drawn with the wedge and the dash in slightly different positions, right? Both of these are S conformers. It's kind of confusing.
The second one's weird because the dash is in front.
Well, let's try it. Okay, we're getting sidetracked, but this is good. All right, so imagine we're a stick man and we're looking down this, right? Let's imagine a second stick man looking down this one. All right, let's do the Newman projections right below. All right, for the left one, we have fluorine sticking straight up. What's to the left? Bottom left. OH. And that means the chlorine must be here. So just like before, we'd say 1, 2, 3. Or sorry, 1, 2, 3. So when we do this, it's S. Let's do the same thing down here. All right, this one, what's sticking straight up? Fluorine. All right, what's to the bottom left? OH. And the chlorine's down here. So we'd say, all right, 1, 2, 3. So both of these are S's, right? But in our original 2D bond line structure, it wasn't immediately clear because you can draw it two different ways. That's why I really like the front half Newman projection view, is it takes a lot of the ambiguity out of that, but you've got to know how to do the proper Newman projection. Make sense? Sometimes students will even say, this is super confusing. Can I just build a model? Absolutely. Build the model, orient it so your lowest priority is sticking behind you, and then determine whether or not you're going clockwise or counterclockwise. That's perfectly acceptable. Yep.
Can you give us the method where you flip two of the groups?
Yeah, so if you read through the Klein textbook, he has this like flip-flop method. Some textbooks do that. If that works for you, more power to you. I've found historically that the Newman projection, because we just learned it, tends to work pretty well for students, but whatever works for you. Yeah. All right, so now what we're gonna do is kind of something a little bit different. Instead, I'm gonna give you the name of a molecule and I want you to draw it with the correct configuration. All right, so for this practice one, draw 1 R, that means carbon 1 is an R, 2 S, carbon 2 is an S, 1 bromo, 2 chloro, cyclohexane. And I'll give you a good trick, all right? This trick seems like the most unscientific thing ever, but I call it guessing and checking. All right? So what I mean by that, and I'll kind of walk you through this, is first draw the structure without any bond line dashes or wedges, right? All right, so I'm just going to go ahead and number my cyclohexane. 4, 5, 6. Sorry, that's a 3. So position 1, we must have a bromine coming off of it, right? Position 2, we must have a chlorine. You notice how I didn't do dashes or wedges, right? All right, so what I'm going to do arbitrarily is just say, all right, carbon 1, what if it's a wedge? If carbon 1 has a wedge coming off of it, is that an R? If it is, leave it. If it's not, what do we do? Flip it to a wedge, or sorry, a dash. So just flip it if it doesn't match what it should be based on the name. So I'll give you a little bit of time to work on this, but see if the guessing and checking method works for carbon 1. Once you solve carbon 1, then move to carbon 2, do guessing and checking on carbon 2. So check with your neighbor too and see if you're getting the same answer. All right, for the sake of time, let's try to do this as a class. All right, so I'll show you what I mean by my guessing and checking strategy. So for example, we know carbon 1, based on the name, must be an R, right? So I'm just going to say arbitrarily, let's guess and check if that bromine's a wedge. All right, so what's the highest priority substituent for this stereocenter, which is carbon 1? Bromine. Okay, so I'd label bromine as position 1. What would be position 2? Would it be the carbon on the right or the left? On the right, because that carbon has a chlorine attached to it. All right, and then this must be position 3. What's position 4? Well, it must be that assumed hydrogen, which in this case must be a dash, right? Because we already have a wedge coming off of that carbon. Okay, so now we can say 1, 2, 3. Is that an R? Yeah, we're going to the right. The lowest priority is a dash. So it just happens I guessed and got lucky. I should have bought a Powerball ticket. All right. So number 1 checks out. Let's do the same thing with carbon 2. Should I go with a dash or wedge? Somebody just throw one out. Wedge. Let's just do wedge for fun. Wedges are easier to draw too. All right. So we've got our second stereocenter off of carbon 2. In the name, it said that carbon 2 is an S, right? All right, so if it's an S, we need to double check. Carbon has a chlorine attached. That's going to be position 1. Between the 2 carbons coming off of that stereocenter, what's going to be higher priority, carbon 1 or carbon 3? Carbon 1, because it has a bromine. Then we do this, and then we also have an assumed hydrogen coming off, sticking back. So if we connect all of these, looks like it's going counterclockwise or to the left. Is this S? Yes. So again, we guessed, we checked, we got lucky. So in this case, this would be the correct drawing for this structure. Yep.
If you have your lowest priority as a wedge and you count it as an S, do you still flip it to an R?
Yes, so anytime your lowest priority is a wedge and not a dash, you need to flip what you assume your rotation to be, right? Yeah. All right, yeah.
Why can't we just say cis infinite?
That's a good question. Excellent question. It's, oh my goodness, it's like I paid you to say that. All right, let's do this. So the question was, why not just use a cis prefix? All right, so underneath this, I drew another cis conformation, right? The bromine and the chlorine are on the same side. They're just both dashes in this situation. All right, so let's really quickly look at this one. We'd say, all right, this would be priority 1, priority 2, priority 3, right? We're going to the right, but our lowest priority is what now? A wedge. So what would carbon 1 be now? Be an S. We need to flip it. So if we look at this one, this would be an S. What do you think this one's going to be based on that same logic? R. So this one's actually not going to be the same molecule. This is going to be 1S, 2 R, 1 bromo, 2 chloro, cyclohexane. If we look at the molecule above and below, do you see how they're non-superimposable mirror images? That means they're not the same molecule. These are referred to as enantiomers. So we can't really use cis or trans with these. And I'll come back and talk about why we have cis and trans in the first place. There are some situations where it's all we have, and so we've got to use cis or trans because R and S can't be applied. Yeah. All right. So now the question is, how can we determine if a molecule is chiral if we have no idea what the structure is to begin with in the first place? That was a really interesting question brought up in the early 1900s. The theory of chirality had been around, but we really didn't know it was true beyond a theory. So we had to come up with some sort of experimental technique. And in order to do this, you have to use something called a polarimeter. And it has a pretty simple concept. You have a light source. This light source goes through a lens that will polarize light. So are you familiar with polarized sunglasses? Right? So those are the same idea. They cut out light that maybe oscillates in the wrong direction. So what it does is it creates plain polarized light. So maybe it's only going up and down, not side to side as a wave. So that up and down wave then goes through a sample. And if you've got a sample in this tube right here, and that sample is chiral, that light that was going up and down might exit the tube going at a different direction or a different angle. So basically it's going to spin plain polarized light. So let's make a note. To be perfectly honest, we're not going to go into the why behind that. That's super physicsy. Yeah. So a polarimeter basically takes account that chiral molecules will rotate plain polarized light.
Is that going to become a test?
Yeah. Just the general concept will be. And there are a few examples of this, but I'll show you what I mean and why this is so useful. Let's take an example molecule, and I'm just going to make up numbers. So in this first one, I have a bromine coming off the top, chlorine here, got a fluorine right here, and I've got a hydrogen here. All right, and then on the right, I have the mirror image of that molecule. Oops, this should be a hydrogen. And the fluorine must be a wedge, right? So this must be a chiral molecule. They're mirror images of one another. They're not superimposable.
The wedge and dash.
Nope, right? Because if you think about this, this is a mirror image. I'm not trying to draw the same molecule twice. It's just a mirror image of one another. So this must be chiral. Because they are non-superimposable mirror images. Okay, so what we would have done in the early 1900s, or even today if we really wanted to, was get a sample of the compound on the left, make sure that it's pure, and then shine plain polarized light through it and see how much that light spins from its original orientation. So maybe it went through going straight up and down, but when it exited like that. Yep.
So didn't you say that it was incredibly difficult to get one set of a chiral just 100%? And how did they do that in the 1900s?
That's a good question. So the question is, how in the early 1900s did they purify one over the other? The reality is they let nature do the hard work. Nature only makes one-handed sugars or one-handed amino acids. So they would look at those and they would see how it spun light. Yeah, so great question. So what they would do is, let's say they take the one on the left in. Is that R or S really quick? So highest priority would be 1, 2, 3. Go like that. Lowest priority is a dash, so this must be R, which means conversely this one must be S, right? But we can always check. Go 1, 2, 3. This one's counterclockwise, so definitely S. Okay, so we've got the R enantiomer on the left, the S enantiomer on the right, and experimentally what they found is maybe this one would rotate the light positive 20 degrees. So it's going to spin 20 degrees in one direction. What do you think the other one's going to do? Negative 20 degrees. And by doing this, they were able to deduce that these are related compounds. They spin light in opposite directions to an equal magnitude, and they referred to these as enantiomers. So enantiomers are mirror images of one another. That rotate light at an equal magnitude. Actually, I should rephrase this. Rotate plane polarized light. At an equal magnitude but in opposite directions. And the key thing is that only chiral molecules can rotate plane polarized light. What do you think happens if you have a non-chiral compound and you put it in that sample chamber? Light will not carry. It'll just go straight through it and come out in that same orientation. Yep.
What if you have a 50-50 mix?
Oh man, these are such good questions. So the question was, what if you have a 50-50 mixture of enantiomers? What do you think will happen? Anybody have a hypothesis or guess?
Same.
They'll cancel each other out. So you have to take into account, if you've got a perfect 50-50 mixture of enantiomers, not one pure compound of one, not one pure compound of another, but a 50-50 mixture, the net optical rotation will be the average of those, which will be 0. So it'll appear to be non-chiral. What do we call that when it's a 50-50 mixture? Racemic mixture. So let's make a note of that. So note, if you have a 50-50 mixture, the rotation will cancel out, meaning no net optical rotation. And the sample is racemic. And this is what they did find for a lot of compounds, was if you have a perfect 50-50 mixture, it actually won't rotate plane polarized light, but it doesn't mean that you don't have chiral molecules in there. It just means you have an equal mixture of enantiomers. So it is kind of this abstract thing. All right, so your problem of the day is actually looking at one of these problems that Emil Fischer in particular was looking at, of, all right, how can we use some of the logic side of our brain to deduce what configuration an unknown compound would be? So for example, I already labeled the stereocenters. Are the positions coming off those stereocenters both wedges? Are they both dashes? Is one a wedge? Is one a dash? How do we know? So I'll let you chew on that over the weekend. Yeah.
How do you spell, is that enantiomers or enantiomers?
Enantiomers, so I-O, yeah.